Here at long last we see the complete board. We'll call it a complete board because there may be tiny little changes to it, but essentially it's doing what it's meant to do. And we built this from scratch, as you've seen in the previous videos. We're running all the programs in one EEPROM here that I have simply blown to be able to use all the facilities to make sure the display works, to make sure the 8-bit input, then the digital to analog converter, and that was meant to be the A to D, but the A to D is now down here. As explained before, these little fellas up the top here are actually ZM427Es. They are all new old stock from 1984 according to the date code, and the whole of them, they all don't work. It's not just me. I'm not one of these people to blame ICs just because my circuit's wrong. After fighting with one of them, I managed to make it work after a fashion, but it just simply wasn't right. I thought, well, it cannot possibly be like this. Then I had the idea of trying another one, and that one didn't work altogether. Then I tried another one, and that worked differently with different problems. In the end, all 7 of them have different peculiarities. Some don't work at all. Some work with some faults. I mean, they are all very strange. Some of them drag the data bus right down so the processor wouldn't run. So in the end I decided to give up, put the 427 aside. I certainly wasn't going to buy another one, and I thought, well, what else do we have? And I found these. I have some of these ZN435s. They're an unusual little device called a multifunction data converter. It's D to A, or you can even turn it into an A to D. It has a counter in it. You can turn it into a waveform generator, all sorts of bits and pieces. I don't think it works particularly well, to be perfectly honest, but it works fine for this project, and there we go. So I can obviously demonstrate it working. This is a pot I've just hung across a very cheap and cheerful power supply, which I built a long time ago. And what we do is we can see on the meter the output. We're looking at the output of the D2A, which is the 428. We're feeding the output of this pot into the op amp, which is in front of this one, as explained before. This one is the octal, actually, with tri-state outputs. Enable us to put that on the data bus, because you can't connect one of those straight up to the CPU, because the data bus is always active in that. There's no way of tri-stating it. Okay, so if we turn the meter on. Let's have them on. Make sure it doesn't time out while we're doing this. Let's just pick a range. It's not completely 0. If we now turn on the turn this down to 0 and switch that on, we now have volts. And if we wind it up, we should see things happening. 0.6, 7.8, 0.9. It's a bit noisy, the thing, as you can see. But let's wind it right up. It'll do up to about 2 volts. That's where the reference is. So you don't really want to try putting any more than 2 volts in it, because this has its own reference. So let's turn that right up. So that's 1.9 volts. So that's just showing it doing its A to D bit. We come down a bit. Let's stop a bit further down. That's 1.4 volts. 1.2. What we're doing here, just a reminder, the program here is setting the word Z80A up in there, and then it goes away. It doesn't go back to the display. Once it's given the instructions to display, it doesn't go for it. Then it proceeds to go between these two, looks at this, puts any output out into there, looks at the A to D, puts it out on the D to A. So basically you can see it's just proving everything works. Obviously you wouldn't have a program like that normally, because it doesn't really achieve a great deal. But let's take that down to 0, and we can effectively say that that project is finished. So there we go. That's using a Z80, how to build a Z80 on a board. And these are suggestions of things you can use. A basic 8-bit output port, 8-bit input port, D to A and A to D. the input, which is the 244, there are actually two wires going in there, which is 1 and 19. If we put the scope probe on 1, you can actually see on the scope this is the enable line going through to enable the input, and there should be 1 on 19 around the back, exactly the same, they're tied together, so that shows that working. This on the other hand, there's just one connection to it, and that is pin 11, and these are the latches, and you can see them quite clearly there. It's just repeating, as I said, the loop is simply looping around, and it's showing whatever is on here immediately goes out to there. That's all the processor does, it just loops between the two. And of course, looking with the logic probe at those actual signals, just to show what it looked like with it. So 1 on that is that. You can see it's just flashing saying there's a clock on it, but using the scope probe, hey, let's do the two together. That's it there, and that, oops, hold it on there, and that's it. You can see that's the equivalent, and the same with the pin 19 would be, sorry, not 19, isn't it? It's 11 there. For the sake of completeness, here is the program listing for the program that I cobbled together to test all the parts of this Z80 computer. Bear in mind it's not written properly with, shall we say, relative jumps, etc, etc. This is simply straight down on paper so we can test the things, then throw it away and never use it again. So if we look at the top, it's often useful seeing what somebody's done, say, to initialize the display. There's not much needed for the 2437, but you can see we run through that. Plus then we output the Z80 and the lowercase a. That's the first part right up to 0017 hex, of course. Then the stack is set, which we're setting at 40FF. That just happens to be an arbitrary figure because it's within the stack RAM. Remember, all these figures, of course, are round the other way. So, of course, FF40 is really 40FF. Okay, I'm sure you understand that anyway. The next bit after the stack is the initialize, or should I say just start, the A to D. A to D converters need to be started, then you have to give them a finite time before the result is ready to be read. So that's why if you look at it, it simply reads, send the start to the A to D, and then you call the subroutine, which is called delay. Now that delay obviously depends on the A to D you put it in. You would obviously optimize it if you're going to do this. Another way of doing it would be, in practice, is you may well use an interrupt so that the interrupt is generated from the A to D when it's ready, and then the processor will jump and take the value from the A to D. In this case, we're not worrying about interrupts or anything. We're simply saying go give it a stretch of time to do it in the subroutine delay, and then look at the result. The jump then obviously at 0022 is C3003B, which is where the next part of the program is, which is the top of the next column. That is simply read in the A to D, and then you immediately, that goes into the accumulator, then you send it out to the D2A, and that's that. The next part at 0040 is read in the IO and then write out to the IO. Once again, this is simply a case of reading something in, writing it out so you can actually see that it's working. Then CA001A takes you back to the A to D, where you're putting the 00 in A and sending it out to initialize the A to D, and that will go on ad infinitum. If anybody is interested in seeing the cobbled together circuit diagram that I used, then this is it. You can see there are lots of changes, additions and whatnots on it. Obviously if you're drawing it out yourself and it's for your own thing you've made, then you probably do a better job than this. This is just in case anybody is really interested in seeing how I connected any particular part up to any of the other parts. That's about all I'll say about that. The second diagram, you can see this is where I did the original circuit for the ZN427s. It all turned out to be faulty, and therefore there's a cross through that saying don't use this. And the ZN435 is at the bottom, and that is the actual circuit that I used for the 435, which you saw working in the video just now. Hope this was of interest to somebody and gives you some inspiration if you're thinking of doing this sort of thing. And good luck, and hope it works. Thanks for watching.